Okay, so we're doing another example from section 5.9, just to add to the variety. In this case, we have an integral that we cannot get the antiderivative for. And we want to know how many subintervals would be needed to guarantee this time that the trapezoidal rule approximation would be accurate to within 1/10,000th. So let me give you a moment to copy the example down, and then we'll look at the solution. Okay. So this problem is similar to the previous problem we did, only this time we're interested in the trapezoidal rule approximation. So what we need to do, of course, is go to our formula sheet for the error bound for the trapezoidal rule. Okay, and if we do that, let me find it here. One moment here. I go back through. Here we are. Now we're looking at this formula here. And the difference between the error bound formula for the trapezoidal rule, you'll notice that the error bound formulas for the midpoint rule and the trapezoidal rule look pretty almost the same, except what's the one difference? Well, the 12. So one of them has a 12 in the denominator, the other has a 24 in the denominator. The fact that the 24 is bigger than the 12 in the denominator tells you that the midpoint rule in general can guarantee more accuracy. It doesn't mean it necessarily is more accurate, but it could, given that we don't know the error, it can guarantee at least a certain level of accuracy. All right, so, but this is the formula we want. We want to use this formula here. So again, we have to find that K value. We have to find that big K value, which is based on the absolute value of the second derivative. Okay, and so, sorry, here we are. So here is our function. Here's f of x. And we have to find the second derivative. So of course, let's find the first derivative. So, okay, f of x is 5 times the cosine of x squared. Then by the chain rule, the derivative of the function would be 5 times negative sine of x squared times the derivative then of x squared, which is 2x. And so you end up getting negative 10x times the sine of x squared. Okay, that's your first derivative. For the second derivative, what I'm going to do is this negative 10 here, I'll bring that out front. And then I'll take the derivative of the product x times the sine of x squared. So I'm going to have to use the product rule and the chain rule, okay, which I do here. And this is going to get me that the second derivative of our function is, well, negative 10 times the sine of x squared minus 20x squared times cosine of x squared. Please let me know if you have any questions. All right, well, what I'll do now is I'm going to factor a negative out. I notice that both of these terms are negative. Both terms of my second derivative are negative, so I can factor the negative out and write this second derivative as negative 10, or I'm sorry, negative times the quantity of 10 times the sine of x squared plus 20x squared cosine x squared. And what I notice is that for the, you see, the x squared, x is between 1 and 0. So x squared is between 1 and 0. And the sine of x squared then, if x squared is between 1 and 0, well, the sine of x squared would have to be positive, because the x squared is your angle, right? X squared is your angle. But if you're, let's see, maybe I can put it in black. You know, if you look at the first quadrant, okay, any angle, I'm going to have to prove this way, any angle from 0 to 90 degrees, which is pi over 2, the sine of any angle between 0 and 90 degrees is positive. Well, pi over 2 is 90 degrees, and pi over 2 is, well, that's 3.14 divided by 2, 3.14 divided by 2, which is about 1.57. So the point is that since x squared is between 0 and 1, since the angle is between 0 and 1 for x squared, depending on what x is, then the sine of x squared would, the x squared angle, x squared is your angle, that's going to be in the first quadrant. And so the sine of x squared would be positive, because the sine of an angle in the first quadrant is positive. Also, the cosine of x squared. The cosine of an angle that's in the first quadrant is also positive. Sines and cosines are positive in the first quadrant. Okay, so hopefully, so this is why I can say, you know, again, yeah, this is why I can make these comments below. this comment here. All the parts, all these little pieces of the second derivative that make up the second derivative are positive. And so this means then that the absolute value of the second derivative would simply be 10 times the sine of x squared plus 20x squared times the cosine of x squared. Okay. Yeah, if you take the absolute value, then the negative goes away, giving you just the positive part. Okay. So this is the absolute value of our second derivative. Are there any questions so far? All right. Well, now that we know the absolute value of our second derivative, now we can try to determine what k is, what that big value of k is. Okay, what big K is. But we always want big K to be easy to get. So like in the previous example, we had a second derivative that was decreasing. So it was easy to determine that the value of K would be the second derivative evaluated at the left endpoint. If you had a second derivative that were increasing, the value, the K would be determined by the value of the second derivative at the right endpoint. Hold on, there's a question here. Why you put the absolute value? Well, so here, this goes back to, hold on here. I got to go back to the formula sheet. It goes back to the formula sheet for the error bound when we determine K. Maybe I'll put this in here. Big K is greater than or equal to the absolute value of the second derivative of x. So even though I have the second derivative of x here, I'm interested in the absolute value. Well, if I were to take the absolute value, okay, if I were to take I want to be a little careful how I write this, but let me rephrase it. There's the second derivative. If I take the absolute value of the second derivative, I'm taking the absolute value of this expression on the right. And the negative goes away, giving us what we have at the bottom. Is that okay, Franklin? Are you comfortable with that?
Yes, Professor.
Okay, very good, very good. Well, now we got to determine K. And here's how you're going to do it. Here's how you're going to do it. Let me show you on the next page. What you're going to do is very simple. You're not going to study whether this absolute value of the second derivative is an increasing function or a decreasing function. You're not going to do that. You're going to notice that when x is between 0 and 1, this x squared here, hold on here, let me do it this way. When x is between 0 and 1, this x squared would be maximized at x equals 1. Okay, again, you're looking for the maximum value of the second derivative. But what about the sine of x squared and the cosine of x squared? Well, the sine of any angle would never be larger than what value? If you think about the sine wave, okay, the sine of any angle is never larger than what value? One. That's right, OPM. If you think about the sine function, right? Think about the sine function here. Okay, this is just a little bit of a, but you know the sine, you know how the sine function acts. It's not perfect, but sorry, then it does that, right? But the sine wave is always between -1 and +1. So the sine function can never get bigger than 1. So I'm going to replace the sine of x squared with 1. Notice I have a less than or equal to here. And the cosine of x squared, by the way, that also, the cosine wave, would never be more than 1. So the rule is when you're finding your value of k, if your second derivative contains sines or cosines, you replace the sines and cosines with 1s. That's the rule. That's what WebAssign's going to want. Okay, you don't want to get fancy. Even though if you were to get a little fancier and maybe draw a graph and really figure out, the maximum value of the second derivative, and technically you'd be correct, but WebAssign doesn't want that. For this class, that would not be the right way to do it. We want k to be easy to get, that big value of k, and whenever we have sines or cosines, we're just going to replace those with 1. Okay, and so 30 is going to be our value of k. That's the value of k that we will use, and that's the value of k that WebAssign will want. It'll want that. And so therefore, the bound on the error for the trapezoidal rule, okay, is equal to, well, 30 times b minus a squared. That's 1 minus, sorry, b, hold on. Now that's 1 minus 0 cubed. Sorry, right. Over 12n squared. That's right. And again, here you have an inequality. You have an inequality. You're going to set the error bound less than 1/10,000th. That will ensure that your error in your approximation, E of t, and again, what is E of t? It always helps to write it out. This E of t is equal to the trapezoidal rule based on n subintervals minus the integral from 0 to 1 of 5 times the cosine of x squared dx. That's what that means. Okay, and so we'll just keep working with it. We'll get 30 over 12n squared is less than or equal to 1/10,000th. And we want to solve that for n. Are there any questions? All right. Give me a thumbs up if you're ready to go to the next page. Okay, Yonatan's good. Mark's good. We'll wait for a few more people. Avery's good. Okay. So here's our inequality. 30 over 12n squared is less than or equal to 1/10,000. And we'll multiply both sides by 12n squared. And so 30 equals 1/10,000th times 12n squared. What we'll do now is we'll divide. By 1/10 times 12. Hold on. There's a comment here. Wait. You know, Jonathan, I'm debating that. Maybe I'm kind of I'm multiplying through and then, well, I want to get the n squared by itself. And you see the n squared here in the top inequality is in the denominator. I'm always uncomfortable when my variable's in the denominator, so I multiply by 12n squared, both sides. But now, you know, I want to have the 12n squared by itself. So why not? Yeah, that. So I guess I could just multiply by n squared. Jonathan's saying at this step here, he's right. At this step here, why not just multiply by n squared? You're right. Thank you. That's absolutely right. Good. Good insight. Good insight. I just creature of habit, I guess. So n squared is greater than or equal to 30 divided by that denominator, and now we take the square root of both sides, and n turns out then, well, the square root of 30 divided by the denominator 0.0001 times 12 turns out to be 115.114. And so it turns out we would need 159 subintervals to ensure our trapezoidal rule approximation would approximate this integral to within 1/10,000th. It makes sense there would be more subintervals. The cosine function, the cosine wave, there's more variability in it. So it might make sense you would need more subintervals to pin down a good approximation. All right, let me give you a moment to think this over. Please let me know if you have any questions. All right, so how many of you like section 5.9. I think it's pretty cool finding these working with these error bounds for these numerical approximation formulas. Uh-oh, I'm not getting too many positive responses. How many think it's interesting? At least, I want to take I don't want my email to interfere. What I mean is I don't want the noise to interfere. Gabriel's okay with it. Thank you, Gabriel. Yantan says it's nice. The homework might be harder. Well, I think I've tried to do some good problems with you. John's not quite as comfortable here. But it's sort of it's the beginning of what's called numerical analysis, and that's very important for computer scientists. I know when I earned my Master of Science in Mathematics, I believe I had to take, I think I had to take numerical analysis. I think it was a requirement. Okay, well, if there are no questions, then I'll stop the recording. All right. All right. Excellent, excellent. Well, this is really now, we've covered section 5.9. And I'll make one more comment, class. So there are other rules like Simpson's rule, and there's an error bound for Simpson's rule, but I think you can apply formulas for that. Apply those formulas based on what you've learned here. So I think you'll be fine. Okay, I'll stop the recording.